Hello and welcome back to another video with It's Dr. Dan, and today we're going to be practicing balancing nuclear decay equations, which you find in nuclear chemistry. We're also going to be going into fission and fusion, and then we're also going to be wrapping this into half-life. So it's going to be a really broad overview of all the different skills that you gain in your nuclear chemistry chapter, really evolving around isotopes and all these different things that you've learned about throughout your semesters, and how to really utilize your periodic table to be able to balance these different equations. So we're going to be looking at mainly all the different examples of this, and then eventually leading up to fission and fusion, and how we can try to figure out what can happen when you have multiple reactions occurring one after another in a chain reaction, one after another. So let's take a look at all these different practice problems. So the first thing is when it comes to balancing a nuclear decay equation, is that you got to remember the law of conservation of mass, is that mass cannot be created nor destroyed. So you have to have the same amount of mass on both sides. Now, when we are doing this, we're always going to be adding up protons and neutrons and really trying to see exactly how much of everything do we have. So for this particular one thing we always want to be practicing is, can you identify what kind of process this is? So we have FR, which is francium, and it's francium 215, and this is also going via positron decay. So as you can see, we have a little beta plus, which represents a positron, and then 0 and +1. So what that means is, when we're looking at this, is the two top parts that are the atomic mass should equal the left-hand side, which is 215. So what we're going to have is 0, and when we add that to 215, we'll see those two numbers will match. So we know that the left and the right equal each other. Now, when we do the same thing for the bottom, right, we see on the left-hand side that it equals a total of 87 on the left. So what does that mean? That the total here should also equal a total of 87. So how would I do that? Well, if we take 87 and then subtract a 1 from that, that's going to be 86. So if I take 86 plus 1, that will be a total of 87. So now what we got to do is figure out, well, what element is number 86? So that's when we go to a periodic table and we have to check. So this is where we got to kind of look all over it and try to find number 86, which we'll see is like all the way down here. So this is radon is number 86. So that is going to be the one that we're going to be using right here. So radon is number 86. So for these, you're always going to need your periodic table. So it will help you kind of really find all the different elements that you probably don't really see that often, because a lot of times these are very, very high number elements in a lot of these equations. Not all the time, but many of them are the ones that are in the F series, the transition states, the very unstable species. So if we have another one, so in this case, we have a beta decay that's occurring. So we have copper 66, and it's going to be going through beta decay. So what that means, we're going to do the same type of thing. So the atomic mass has to be the same on both sides. So being that we have 66 on the left, we should have a total of 66 on the right. So we see that 66 plus 0 is equal to 66. And then on the bottom, we have 29. So once again, our entire right-hand side should also be equal to 29. So if we try to do some little math here, how can we get 29? Well, if we do 30 minus 1, that will give us 29. Okay, so we're going to be adding up all these little pieces to try to make the left and the right equal each other. So once again, what are we going to do? We're going to go to our periodic table, and we're going to be trying to find element number 30. And what we can see is it's always going to be really close to where you started. So we have copper that's right here, but you can see that right next door is number 30, which is going to be zinc. What element or what nuclide that we're going to be starting with, right? So it says that we have 129Te, so this is your parent nuclide. And what it's telling us is that it's going to go through alpha decay, which, if you remember, we represent by a helium atom, which is 4,2 with an He. And if you don't remember all these, go to my different types of reactions video to help review all these core concepts. Now, we want to know is what will we create once this breaks apart? So we're going to be creating a new species, just like how we had in the previous problem. So the one thing that we got to do is kind of fill in all the missing boxes, right? So you got to have an atomic mass and an atomic number for every single element here. So we got to fill those in. So the first thing we should do is let's fill in tellurium. So Te is all the way down here. This is tellurium. So you can see it's right here. So this is number 52 on our periodic table. So what we're going to do here is we're going to write in a big 52 to match our periodic table. And now what that's going to tell us is that, okay, the entire bottom, all the atomic numbers should have a total of 52 because the left and the right should match each other. So how do we get 52? We do 50 plus 2, and that's going to give us the identity of our element. Now, when we do our next part, well, we got to remember that when we're looking at all these different pieces of the puzzle, trying to figure out what our element is, well, we got to also add up our masses as well. So being that the left-hand side is equal to a total of 129 for the atomic mass, that means the right also has to equal up to 129. So if I take 125 plus 4, that equals 129. So now what I'm going to now do is look for number 50 on our periodic table. So it's kind of a game where you're always trying to find all the missing pieces. And then we can see that tin is really close to it, which is 50, which is the identity, which we go off the number of protons in our nucleus. Okay, so that's one thing to kind of keep in mind, is that when we're looking at all these, we can always see that everything is kind of changing, right? So we have 50 protons here, 52 protons, and we also see the number of neutrons is changing as well. So we have 75 neutrons on this side, and then a total of 77 neutrons on the other side. So you see that lost 2 neutrons, 2 protons in this transition. So you can always kind of count to make sure that everything's equal, especially if to figure out some of those harder problems, which might involve subatomic particles and counting everything. It goes back to your basics of, can you read a periodic table and answer all these questions? So our next problem is write the nuclear equation for iron 59, which undergoes beta and gamma emission simultaneously. Okay, so being that we have iron 59, so the first thing is, being that's written that way, what that's telling us is that is the mass of iron, right? It's not referring to the number, it is the atomic mass of this radioisotope. So we're going to write iron 59. And it's telling us that we're doing 2 different emission processes at the same time. We have a beta emission, so that's 0, -1. And then we also have gamma emission. And these are the kind of things I would really recommend kind of memorizing for your exams, because it's usually you're not given these for. They are pretty easy symbols to remember, but it's still one more thing to kind of add to the puzzle. So now what we're trying to do is figure out is what is our missing pieces. So we're trying to figure out what is the daughter nuclide that is created. And remember, the left has to equal the right. So the first thing is we should do is we should look up iron, right? So iron is number 26 on our periodic table. So we're going to end up kind of writing that down for ourselves, seeing that that is number 26. So once we write that in, just to kind of fill in that gap, so 26, that means that all the numbers on the bottom here, adding up all 3 of these, should have a total of 26, and the entire total of the atomic mass should be equal to 59. So if I am to do that, well, the nice thing is on the bottom, how do I get to 26? Well, if I do 27 plus -1, that's going to give us our missing number. So this is going to be an atomic number of 27. Now, being that everything is zeros on the top here for all of our masses, that is really easy math. So all we have to do is just fill in that missing number there, which is going to be 59 for our missing box. So 59 will be our mass. So let's try to figure out what number 27 is. So it's going to be really close to iron. So it's going to be right next door to it. And I have it kind of covered up with my box. And you're going to see that it is cobalt. Cobalt is number 27. All right, so we're going to fill that in, that we have cobalt. And now, well, what is exactly happening here in this process? Well, the one thing when you have a beta decay, it's going to be changing your protons and neutrons around. And then gamma emission, it's going to be releasing a high energy photon. So, well, what exactly is happening here? Well, if you count your different subatomic particles, right, you have 26 protons that are here. And then you can calculate how many neutrons there are by subtracting it by the number of your atomic mass. And you'll get that there's 33 neutrons in iron. So if you look now at cobalt, well, how did the entire picture change? Well, you have 27 protons over here. So what you're going to have is a neutron is going to convert into a proton. So you see that the neutron count went down and then the proton count went up as a result. And that's beta. So with positron, it's the opposite. Instead, a proton is going to be converted into a neutron instead. And that's where that positive particle comes from in when it's releasing that antimatter. Let's take a look at another example. Sometimes you're going to have bombardment reactions, which is a really common reaction that's done in synchrotrons around the country and around the world. So what a synchrotron is essentially when you have particles that are accelerated very, very fast, essentially approaching the speed of light across miles. So there's these facilities around the world. There's one at CERN in Switzerland and another one in Berkeley in California that accelerate different particles to try to see if they can collide them with each other to see if we can make new elements. So one of the things is that when you have these collision problems, it's a little bit more involved because you'll have multiple reactants and also multiple products because pieces are going to be breaking off. We're going to be splitting the atom essentially. So what we're going to be doing is the same idea is we're going to be adding up the top and the bottom, right? So when we do this, we usually always have one complete side. So what you can see on the products is we have both products here. So we have argon, it's colliding with something, and it's going to be breaking down into a potassium 43 and a proton, right? So this guy, I know it shows hydrogen, but we always think of this as a proton. So whenever we are looking at that species. So we have a total of 44 as our mass. So that means we need 44 on the left as well. So being that we have 40 on the left, if we do 44 minus 40, that tells you you're missing a total of 4. Now on the bottom, we have a total of 20 when we do 19 plus 1. So that means we need 20 also on the left-hand side too. So if we do 18 plus 2, that's going to be a total of 20. So which subatomic particle or what element does that represent? Well, one thing that you can realize is, hey, that's helium, right? So helium or an alpha particle. So that tells you a really big, heavy alpha particle collided with argon to break it into potassium and hydrogen. So sometimes you have word problems and it doesn't give you all the little pieces. So let's break down this word problem. So it says carbon 11 is bombarded. Okay, so being that we have the word carbon 11, let's start by writing that down. So we know it's C11, and you know that its atomic number is 6 from the periodic table. Now, when it says it's being bombarded, that means it's colliding with something. Something is reacting with it. Okay, so those are like those little buzzwords. So we'll put the word reacting just so it's something that you're familiar with. Now it's saying it's colliding with a helium-4. So it's telling you that, all right, we're going to be reacting with another helium. And then it says, as a result, we're going to be making a proton. So we see that we're making a proton. So what we'll do is we'll draw an arrow. We'll put a single proton here. And one other particle is produced. Okay. So what we're trying to do is figure out is what is the other particle. So with that being said, what we're going to do is the same process that we've been doing before. So when we look at this, we're going to add up what we have on the left side this time. So when I add up my masses, I have a total of 15 on the top. And then when I add up my atomic numbers, I have a total of 8. So this is going to be what we're going to have also on the right-hand side. So we're going to have a total of 8 on the bottom as well. So that means how do I get to 8? Well, we do 7 plus 1. That will give us 8. So we can see that we have that total. And then when it comes to the bottom, well, how do we get to 15? Well, we got to do 14 plus 1 is going to give us 15. Okay, so we have that same total. Now, which element is number 7? Well, what's one away from carbon? And it's nitrogen, right? So when we take a radioactive carbon, hit it with a helium or an alpha particle, it's going to make a stable nitrogen. Remember, the goal of all nuclear decay is to make stable isotopes eventually over time. So that would be our answer. Let's take a look at another example. Gallium is used for the detection of pancreatic cancer because it's taken up by tumors. The emission of positrons allows the tumor to be located in when it comes to medical imaging. So let's first write the balanced equation for this. So what it tells you is that we're going to have gallium 68 is what's going to be used here. So let's first write that down. And then it says it's going through positron emission. Well, when we're doing something with positron emission, that's going to be 0 and +1 with a beta plus. And now we wanted to try to figure out as well what species is going to be created. Well, the one thing we can remember is, well, the tops are going to be equal. So that's a pretty easy one, being that a positron has no mass. So that means the mass of our new particle is also going to be 68. Now, you're probably trying to think of, well, what's the atomic number for gallium? Well, that's why we have periodic tables. We look these things up. So the one thing is you can see gallium is right here. It has a mass of 31, or sorry, not a mass, atomic number of 31. So what we are going to do is we're going to write a 31 here. So that means that the entire bottom of this should equal to 31 as well. So if I take 30, add that to 1, we get 31. So which different element is 30? So we're going to look right next door and we see, hey, look, it's zinc. So zinc, again, zinc 30 is going to be our isotope here that is going to be made. Now let's try to combine this kind of problem with something else that we've done before in the past, which is half-life reactions. So when it comes to trying to do these kinds of reactions with medical imaging and different practices, we have to consider how long does it live within the body or within our world before you choose it for something that could last for maybe just a few minutes or a few hours or days or years or millennia, right? We have to consider how long does it live. Let's take a look. So with this problem, if the half-life of the reaction above is 68 minutes, how much of a 64 microgram sample is active after 136 minutes? So half-lives, they tie into these types of radioactive decay as well. To remind you, what was a half-life? The half-life of a radioisotope is the time for the radiation level to decrease or decay to half of its original amount. So every single radioisotope has a time frame where that occurs. So what that means, after every half-life, it's going to decrease by half. So if I start at 100% of my sample, I'll have 50, then I'll have 25, then I'll have 12 and a half, and it'll keep continuing, right? It'll be half, a quarter, an eighth, and so a 16th, and so forth for every single half-life that passes. It's going to be very, very little in the end. So let's try to solve this problem that we were just looking at. So the first thing that we got to do is we have to write out, well, how much sample did we have? And it says that we have 64 micrograms of sample. So what we're going to do is we're going to write out our half-lives and try to see, well, when do we get to 136 minutes? So the one thing is that you could do is we could simply just take that 136 minutes and then see if it divides cleanly into our half-life time, which was 68 minutes. So if we do that, right, we see we have 68 minutes. We see that our total time passed was 136 minutes. So all these things can be used. So if it divides cleanly, then we can do this a lot simpler, right? We don't have to use these fancy kinetics equations that you learn about in Gen Chem 2, right? That's beyond the scope of this course. So what we'll do is we need to have two half-lives. So after the first half-life, it's going to divide by half. So what we have is 32 micrograms after one half-life. Now after the second half-life, you're going to divide that in half again. So 32, divide by 2, and then we'll have a total of 16 micrograms. And that's going to be how much is left and remaining inside your sample. So it's all about, well, how much is active? It's going to be 16 micrograms, and it went through 2 half-lives when that happened. And so essentially you can kind of see is that each part, right, we had a half of our sample at the middle. And now we're down to a quarter of our sample after the second half-life. And then if you went through another one, it'd be an eighth, then a 16th, and a 32nd, and so forth. It's going to keep getting smaller and smaller and smaller. Let's look at another example. Technetium is used in over 80% of all nuclear medicine procedures. The isotope has a half-life of only 6 hours, so it makes it really good for something when you have to do medical imaging, or if you want to keep a patient overnight for observations, or to bring them in over multiple times over the course of a week. You can really track the progress of how this isotope will work. Now, if the patient is given a dosage that has an activity of 8.0 millicuries, when will the activity become 0.50 millicuries? Now, what the heck is a Curie? I never talked about that in any video. Well, let's look at it real quick. There are units when it comes to actually talking about radiation for when we're trying to understand some of the basics. I wrote some of them here. The first one is the activity. So when we talk about activity, we usually look at it in two different units. The common unit is a Curie, named after Marie Curie, the woman who founded and won the Nobel Prize for radiation and discovered multiple radioactive elements. So what it means is one Curie tells you how many times an isotope is disintegrating over a course of a second. So usually it's always how much is a gram disintegrates within a second is usually the way that's always referred to as. So what we say is 1 Curie is equal to 3.7 times 10 to the 10 disintegrations per second. Now, there's also the SI unit, which is a becquerel. So whenever we use a becquerel, it's a BQ, and then 1 becquerel is equal to 3.7 times 10 to the 10 disintegrations per second. There's also absorbed doses. So one is if you've ever seen like the Fallout show, which is really popular right now. And then probably in a few years that might be a dated reference. But right, the absorbed dose is referred to as a rad. So how much radiation have you absorbed? Or if you have a gray is the SI unit. So it's joules per kilograms of tissue that absorbs. So it's the energy absorbed. Now, does that mean you have to do any crazy calculations? You can treat them the exact same way that you did with grams or any type of sample you had before. It's still going to be half of what's there. So, being that it wants to know how many half-lives occurred in order to get from 8 to 0.0, what 0.5, what we're going to do is map this guy out. So we have 8.0, then we'll go into half, we'll go down to 4.0. We'll do half again, that's going to be 2.0. Okay. Now we'll do another half. We're dividing that by 2 one more time, right? And we have 1.0. Now if we divide 1 by 2, we'll have our 0.5, which was our goal. Now the question is, well, how many half-lives is that? Well, we'll count them, right? We have 1, 2, 3, 4. So you count each of those arrows. Now you got to keep in mind, every single one of those half-lives is 6 hours. So we're going to have 6 plus 6 plus 6. So how many total hours have passed over the course of time? You'll add them all up and you'll see that 24 hours have passed in order to go from 8 to 0.5 millicuries. Okay, so that's going to be MCI is what that unit is. If you ever see a Curie, you can treat it like a gram when it comes to a half-life calculation. It's going to still be divided by half the whole time. Now it does have a different meaning to it, but you can treat it the same when you're doing these calculations. All right, now let's go on to a different type of problem altogether. So with nuclear fission, so this type of topic is something that's completely different than anything we've looked at. This one I think is just a little bit something extra, so that way you know what the difference between fission and fusion is. So nuclear fission is essentially what has caused the atomic bomb, and it also is what causes us to be able to power nuclear power plants. So it goes from either energy or a weapon of mass destruction. And being that Oppenheimer is such a big movie right now, it's kind of cool to be able to kind of get an idea of what the basic idea of the science is. So what's actually occurring within the bomb? What do they actually have? Well, the whole idea is that inside of it, there is a bunch of uranium that is inside. And this is essentially uranium-235. And then it's sitting inside the container. It's not going to do anything just being in there. The thing is, it needs to be activated. Now, how is that actually done? Well, what happens is they essentially shoot a neutron at the uranium atom or isotope. When that happens, then it becomes unstable. The entire thing cannot last in this condition. It's going to explode and release a ton of energy as a result. So once that neutron gets shot in there, it's going to be really unstable. And the goal is to make stable isotopes. So it's going to split into two completely different isotopes. And in the process, release three different neutrons as a result. Now, is that something that's so crazy, right? It releases a ton of energy as a result, but is that all? Well, essentially, the way that that works when it comes to a bomb is it's all about a chain reaction. And the same thing if you want to actually cause a nuclear reaction within a reactor to produce energy. It's all about, well, once I have the first one, can I have the reaction keep going, right? Where it keeps increasing, right? So if one goes and they release neutrons spontaneously, can it hit another set of uraniums, which will then cause it to cascade and cause more of these different elements to split, releasing more neutrons, and that will keep going over and over and over again, having many of these different reactions. So what the whole idea is when it comes to creating nuclear energy is it's all about the rapid increase in the number of high energy neutrons that are created, right? So every time when you have one, it will split into three, which will split into another set of three. So you can kind of see it's like a cubed function of how fast this thing is going to grow. Now, in order to sustain this reaction, all the uranium must be brought very, very close together, right? So if you think of like the uranium nuclear bomb, it was all kept in a very, very tight capsule in order for it to go very, very fast and release a ton of energy all at the same time. So now when it's all brought together, this is what's referred to as the critical mass, meaning that essentially we're going to have an almost immediate collision with more neutrons. Now, when it comes to a nuclear reactor, is it going to explode? No, it's in a controlled process. So that way it's a continuous set of collisions and it'll keep releasing energy. Every time these different elements split, you're going to be releasing energy, which can be harvested and used. As long as everything's cooled down and properly maintained under safety conditions, we can use it. So it's all about hitting it with a neutron and splitting. So it's just something a little bit different to learn about. Let's learn about fusion. So when it comes to fusion, the whole idea here is this is actually what causes our sun to shine bright and the stars around us. So this is a little bit of a happier one, but it is something that releases a ton of energy. The sun releases so much energy that you can feel it from Earth, right? We are many, many millions of miles away from the sun, and you can feel the heat coming off of it. It releases a lot of energy. So the whole idea here is when you have two small nuclei that combine to form a bigger nucleus. Now in the process, there is mass that is lost, but it's all converted to a massive amount of energy. Now this is much more than fusion. It's not even close in comparison. In fact, when it comes to fusion, it requires temperatures around 100 million degrees Celsius. Keep in mind, when it comes to the Earth, generally we're anywhere from like 0 to like 40 degrees C typically in most climates. That's a lot. So now the whole reason it has to be that hot is that it needs to overcome the repulsion within the atoms because we're fusing two different nucleuses together. That's extremely difficult to do, especially under depending on the conditions. Now, when this happens, this reaction is occurring continuously in all stars and suns. So once it starts, it doesn't stop. So this is something that will keep going for a very, very long period of time. Eventually it can run out, but that's something that takes millions and millions of years. So the whole idea with this reaction is when you take isotopes of hydrogen and then they react together. So if you didn't realize, there are three different major isotopes of hydrogen. There's the normal one with just one proton, but there's also deuterium, which has an atomic mass of 2, has 1 neutron, and then tritium, which has 2 neutrons, and then the 1 proton to it. So when tritium and deuterium combine together, they're going to make a helium atom and release a neutron and a ton of energy in the process. Now with that, that is what the whole idea of fusion is. So let's see if we can do one practice problem and see, can you identify the two different types of reactions? So if I ask you just to classify which one is fusion or fission, could you do it? So the idea is when it's fusion, you have two different nucleides coming together and it's going to be making something, a bigger nucleus. When it's fission, you have a neutron being shot at it and it's colliding with it. So with this case, right, on this first one, you see that we have these two small nuclei coming together, fusing together, right? It has to be small nuclei. So in this first example, being that we have two heliums, this is what we consider as fusion. They are coming together and it's releasing some protons in the process. Whereas the second one here, you can see a neutron is being shot at a uranium and it's splitting into different isotopes and releasing neutrons, which will continue to chain react. So this one is fission. Luckily, I'll never ask you guys in my class to ever balance these things. They're a little too major for that, but it's good for you to be aware of them because they can be asked on homeworks and quizzes and sometimes on exams in the final. So just be aware of that these two exist. All right. So this has been my practice problem video. So went over everything that you need to know for when it comes to nuclear chemistry. I hope that it helped going over many different types of examples. Hopefully it prepares you for your homework and your exams and all these other different things. And I hope you got to learn something new with this chapter. So this wraps up nuclear chemistry. So once again, thank you so much for listening. I hope that this video helped a little bit for you to kind of wrap up those loose ends. And if you did struggle with watching it, I recommend watching it, try solving it, pausing while you're going through it. It'll help you really figure it out. And thank you once again. If this is your first time here, please hit that like and subscribe button, and I hope to see you again in the future. All right. Thanks all. I hope you have a wonderful day. I'll see you later. Bye now.